Hey guys, how's it going? Mr. Mitchell here. In this video we're going to go over 4 worked examples to show you how to do problems involving diffraction gratings and the grating equation. Now if you haven't already done so, check out my previous video covering the theory on this topic, and that way you can apply what you learned in that video to this one. So let's get started. Question 1 says a manufacturer claims that a grating consists of 3.00 times 10 to the 5 lines per metre and is accurate to plus or minus 2.0%. A technician decides to test this claim. She directs laser light of wavelength 633 nanometers onto the grating. So in the picture here you can see the laser light is passing through the grating. We've then got an angle to the third order maximum, which is 35.3 degrees, and we've got our list of maxima on the screen. Then says she measures the angle between the central maximum and the third order maximum to be 35.3 degrees, as we've just seen. Part A says calculate the value she obtains for the slit separation for this grating. So writing down what we know from the question, we're trying to find the slit separation D. We know that angle theta is 35.3 degrees, the order number m is 3 since we're at the third order maximum, and the wavelength lambda is 633 nanometers, which we need to convert into meters, so that becomes 633 times 10 to the minus 9 meters. Writing down the grating equation, we have d sine theta equals m lambda. Substituting in the numbers gives d times sine 35.3 is equal to 3 times 633 times 10 to the minus 9. Then doing the right hand side in your calculator divided by the sine of 35.3 to get d on its own, you should get an answer for d of 3.29 times 10 to the minus 6 meters. Part B says what value does she determine for the number of lines per metre for this grating? Well, here we need to use the relationship between the slit separation D and the number of lines per metre. And remember we saw this in the theory video for diffraction gratings and the grating equation. So we have D equals 1 over the number of lines per metre, where remember we want to find the number of lines per metre here. So let's substitute in D that we just found in part A. So we have 3.29 times 10 to the minus 6 equals 1 over number of lines per metre, and therefore to get the number of lines per metre on its own, we can actually just swap these two variables round because this is on the denominator and this is essentially on the numerator of this side. So we end up with the number of lines per metre is equal to 1 divided by this value, and if you do that in your calculator you should get an answer of 3.04 times 10 to the 5. Part C says, does the technician's value for the number of lines per metre agree with the manufacturer's claim of 3.00 times 10 to the 5 lines per metre plus or minus 2.0%? Well, what we need to do firstly is find the upper and lower limits of the manufacturer's claim. So to do that, we firstly find 2% of 3.00 times 10 to the 5, and you can do this percentage in whatever way you're familiar with, but I tend to do this first, so I do 0.02, just dividing 2 by 100, and then times it by 3.00 times 10 to the 5. And if you do that in your calculator, you should get plus or minus 6 times 10 to the 3, which is the same as plus or minus 0.06 times 10 to the 5. Notice how I've rewritten this in terms of times 10 to the power of 5, because that's what the value is here, and I want to see how this will compare. So to find the upper limit, all we need to do is take this 3.00 times 10 to the 5 and add on our 2% value. So doing that, because they're both times 10 to the 5, all we need to do is add on this 0.06 to this value. So we get 3.06 times 10 to the 5 lines per metre, or you can do that in your calculator if it's easier to see. And then we can find the lower limit by just taking away this value this time. So we do 3.00 times 10 to the 5 minus 0.06 times 10 to the 5. And just by looking at it or doing it in your calculator, you should get a value of 2.94 times 10 to the 5 lines per metre. And therefore we can say the technician's value does agree with the manufacturer's claim, since 3.04 times 10 to the 5 falls within the range 2.94 times 10 to the 5 to 3.06 times 10 to the 5. And remember that 3.04 times 10 to the 5 value came from the answer to part B. Question 2 says a laser produces monochromatic light of wavelength 589 nanometers, which passes through a diffraction grating. The grating is 200 lines per millimetre. So here's our monochromatic light passing through the grating, and then we've got our angle to the maximum theta and our maxima on the screen. And part A says what is meant by monochromatic light? Well, remember monochromatic light is light of a single wavelength or frequency, i.e. one colour. Part B says calculate the angle theta between the central maximum and the third order maximum. Well, to find the slit separation D, we first need to determine the number of lines per metre. And in the question here we're given the number of lines per millimetre. So remember, to get the number of lines per metre, we take the number of lines per millimetre and times it by 1000. So in this case we're told there are 200 lines per millimetre, so we times that by 1000 to get 200,000, or 2 times 10 to the 5. And then we can use the relationship between slit separation D and number of lines per metre to find what D is. So we have d equals 1 over the number of lines per meter, which is equal to 1 over 2 times 10 to the 5, and if you do that in your calculator, you should get an answer of 5 times 10 to the minus 6 meters. And now we're in a position to calculate the angle theta. So writing down what we know from the question, we're trying to find the angle theta. We know the slit separation d is 5 times 10 to the minus 6 meters from here. We know the order number m is 3, since we're talking about the third order maximum here, and it's also in the picture. And we know the wavelength lambda is 589 nanometers, which we need to convert into meters, so that's 589 times 10 to the minus 9 meters. So writing down the grating equation, we have d sine theta equals m lambda. Substituting in the numbers gives 5 times 10 to the minus 6 times sine theta is equal to 3 times 589 times 10 to the minus 9. And to get sine theta on its own, we need to do the right hand side divided by the 5 times 10 to the minus 6. So doing that in your calculator, you should get an answer for sine theta of 0.35 and then lots of other digits. And then to find theta, we need to do inverse sine of both sides. So doing shift sine or inverse sine in your calculator should give you an answer for theta of 20.7 degrees. And you could round that up to about 21 degrees if you like. Part C says a series of maxima and minima is observed. Explain in terms of waves how a maximum is produced. Well, remember, a maximum or point of constructive interference is produced when the crest of one wave meets the crest of another, or when the trough of one wave meets the trough of another. Trough meets trough. Part D says the monochromatic light produced by the laser is yellow. This laser is now replaced by a second laser which emits blue light. Explain why the observed maxima are now closer together. Well, firstly, we can say that blue light has a shorter wavelength than yellow light. And rearranging the grating equation for sine theta, we can say that sine theta is equal to m lambda over d. And then ignoring the m and d, we can see how sine theta is related to lambda. We can say they are directly proportional. So we have sine theta is directly proportional to the wavelength. So we can say therefore, as wavelength decreases, sine theta and therefore theta decreases, so fringe spacing decreases, meaning the maxima are closer together. Question 3 says a beam of parallel monochromatic light is incident on a grating. An interference pattern is produced on a screen. The edges of the screen are at an angle of 40 degrees to the centre of the grating as shown. So our monochromatic light is incident on the grating, and then we've got two angles of 40 degrees labelled here and our screen at the side. And it says the wavelength of the light is 420 nanometers and the grating spacing is 3.27 times 10 to the minus 6 meters. Determine the total number of maxima visible on the screen. Well, here we want to find the order number m. We know that slit separation d is 3.27 times 10 to the minus 6 meters. We know the angle theta is 40 degrees because looking back at the picture, remember the angle theta is the angle from the central maximum to whatever maximum you're interested in. So that's going from the centre up to this maxima or the centre down to this maxima. We then have the wavelength lambda, which is 420 nanometers, and that's the same as writing 420 times 10 to the minus 9 meters. So writing down our grating equation, we have d sine theta equals m lambda. Substituting in the numbers gives 3.27 times 10 to the minus 6 times sine of 40 is equal to m times 420 times 10 to the minus 9. And then doing the left hand side divided by the 420 times 10 to the minus 9 in your calculator should give you a value for m of 5. And therefore we could say that 5 maxima will appear above the central maximum and 5 maxima will appear below it as shown below. So here's the part of the diagram showing the screen, and I'm just going to label on the maxima to show you how many we'll have in total. So remember, we're going to have our central maximum in the middle, and then we need to have 5 above it. 1, 2, 3, 4, 5, and then we also need to have 5 appearing below it. 1, 2, 3, 4, 5. So therefore we could say our total number of maxima is 11. And then the 5 that we've calculated going above and below the screen. And remember, that's because we said in one side in one of the triangles we have 40 degrees, and that corresponds to m equals 5 maxima. So in this region we need 5, in this region we need 5, and then we've got the central maximum which totals 11. Lastly, question 4 says light from a laser is shone onto a grating. The grating is 100,000 lines per meter. An interference pattern is produced on a screen as shown. The angle between the central maximum and second order maximum is 14 degrees. Part A says to calculate the wavelength of the laser light. Well, first we want to find the slit separation d using the number of lines per meter. So we don't need to multiply by 1000 here, remember, because we've not got number of lines per millimeter, it's number of lines per meter. So we don't have to do as much work. So to find slit separation d, we do 1 over the number of lines per meter, which is 1 divided by 100,000, which is equal to 1 times 10 to the minus 5 meters. And we now want to calculate the wavelength. So writing down what we know from the question, we're trying to find lambda. We know that slit separation d is 1 times 10 to the minus 5 meters from what we've just found. We also have the angle to the maximum theta is 14 degrees, and the order number m is 2. And we can see this by looking back at the picture. So there's our central maximum, and then we've got the first order maximum and second order maximum there. So that's where our line's going to. So writing down our grating equation, we have d sine theta equals m lambda. Substituting in the numbers gives 1 times 10 to the minus 5 times sine 14 is equal to 2 times lambda. So doing the left hand side in your calculator and then dividing both sides by 2 to get lambda on its own gives a value for the wavelength of 1.2 times 10 to the minus 6 meters. Lastly, part B says what happens to the angle between the central maximum and second order maximum if a grating of 200,000 lines per meter is used instead. Well, if we think about this relationship that we use to calculate the slit separation D, remember this is equal to 1 divided by the number of lines per meter. So if we were to double the number of lines per meter from 100,000 lines to 200,000 lines, then notice how that decreases the slit separation. So we're increasing the denominator of this fraction, which will decrease the value of D. So we can say as the number of lines per meter increases, D decreases. And then we can rearrange the grating equation to think about how D is going to affect the angle. So since D sine theta equals m lambda, we can rearrange for sine theta by dividing both sides by D to get sine theta equals m lambda over D. And then we can ignore the m and lambda and say that sine theta is directly proportional to 1 over D. And we've just said that doubling the number of lines per meter will decrease the slit separation D. So we can say that as D decreases, sine theta increases, and so theta must increase as well. i.e. the angle to the maximum theta increases if we double the number of lines per meter. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a thumbs up, subscribe to the channel, and I'll see you in the next one. Take care.